This is the uncertainty principle. Yikes. He must be really sleepy. So, what is the uncertainty principle? Well, let's say you're doing an experiment with a rope for your physics class. So you take it and you pulse it once, then you pulse it again, then you pulse it a third time, and so on and so forth. And eventually, a man comes up to you from behind you and he asks you, tell me exactly where the wave is. And I mean, you can't tell him because it's spread out over this huge area. You could tell him at this point in the park, or at this point in the park, or at this point in the park. I mean, all of them are accurate, but none of them are precise because clearly they're so far away from each other. You're not getting any real accurate measurements. Then he asks you, what's the wavelength? But you can clearly answer that because, it's a periodic wave. Then the next day, you do the same experiment, but you only pulse it once. This time, you can give, when he asks you for the position, you can give a very accurate answer as to where the position is. But when he asks for the wavelength, I mean, it's not periodic. What wavelength are we even supposed to look for? Is it this wavelength? The wavelength extending to the non-existent next cycle? What is he asking for? And so, you can try to construct waves in between that have both a sort of defined position and wavelength, but you can even construct something like this, which comes to a peak here and slowly goes away. And maybe you can say, its position is here, but how does that diminish all the stuff that's going on the other sides? And maybe you can say, oh, well, the wavelength is this much, but it's not really periodic, is it? So, that's the basis of the uncertainty principle. You can't know both position and wavelength. Oh, which acts kind of like momentum, but for wave functions, of a wave function at the same time. You can't know both of these. I mean, you can know one of them with astounding precision, so you measure it again and again, and you get 0.562, 0.561, 0.564, 0.563. But then you look at your wavelength measurements and you see 3.212, 5.117, 10.229, 117.017. And as you can see, also note that doesn't mean that these measurements are getting less accurate. You can still see 3 decimal digits on each one. It's that they are nowhere near each other. The standard deviation is going to be much higher for the wavelength than it is for the position. In the same way, you can flip them around by getting really accurate measurements of the wavelength, but then you'll get crazy measurements of the position. And then you can also go middle of the road and have both of them be mediocre. Both bad. But you can never have both of them to perfect precision. And note, once again, you'll still get the same amount of decimals. You can see, once again, note that there are 3 decimal digits on each one because there's no drop in accuracy. You're still getting perfectly accurate measurements. It's just that the measurements are going to stabilize in wildly different positions each time you measure them, whereas for wavelength, they're going to stabilize in pretty consistent positions. On that topic, From experimental data, it looks like measurement is like electrically shocking the particle we're trying to measure, because the particle's wave function seems to suggest it could be anywhere, but as soon as we actually measure its position, it gets electrically shocked into being sort of a delta function, where its probability of being in the place that it was measured to be in is extremely high. But then, as longer and longer periods of time pass without a measurement, it slowly goes back to stabilizing. But then, if you measure it again, you might get a wildly different measurement, but the probability of the particle being in the place that you got for your measurement is going to be stunningly high again. What this means is basically, it's not a weakness of our own measuring tools. It's not a weakness of our own measuring tools that we're not able to. If you try to get one of the measurements down, the particle will stop cooperating with you on the other measurement. If you try to get the other measurement down, the particle will stop cooperating with you on one measurement. And you can never get both measurements down, but you can get the particle to cooperate with you at varying levels of accuracy on both measures, but you can never get it to cooperate with you perfectly on both measures. So that's essentially what the uncertainty principle is all about. The particle doesn't want you to know both its wavelength and its position at the same time, and if you get one of them right, it's going to spaz out on the other. That's it. Thank you.